Okay, cool. Recording. Okay, so for those, I guess I don't know if anyone here is new, but we had sort of finished going through all of like the first eight chapters of this book, which covers the so-called, tabular learning methods or methods for problems where you can enumerate all of the state action pairs. And that's sort of the like because you can define all the state action pairs, there's a number of techniques that you can use, which you can't use if the state space is too big. And that's what part two is for. So but the whole book anyway deals with, so-called Markov decision processes, which are defined by this thing called the probability transition function, which tells you for a particular state action pair, what is the probability of all of the transitions, which would be a new state and a reward value obtained during the transition. So in the tabular case, we could actually form like a list of all of these transitions and just have like a matrix or like whatever, array structure of these probabilities. But in general, this function could just be like a function where it would give you the probability, but you can't necessarily actually like write down all the values, especially if the action or state space is even continuous. In that case, it could be actually infinitely big or just too big to manage. But um, when you actually interact with an environment, you end up with this sequence of states, actions, and rewards. And which states, actions, and rewards you actually obtain, will depend on the probabilities in this function. And also in this first section, we pretty much only deal with episodic problems, which are problems where there's some starting state and then there's some trajectory through the environment that will end at some terminal state, which here, this is like a little cartoon of like what the book refers to as these backup diagrams, where the white circles are states, the black circles are, actions, and then rewards would be obtained, on somewhere along this arrow, along the way to the next state. And then this square is reserved for a special terminal state. And here, what makes the terminal state special is, here, I'll just make this a little larger, is that the probability um, of transitioning out of the terminal state is always zero. So you can see like this probability is one for the transition state being the terminal state, whatever that is. I mean, this could also be a set of states, but in general, like once you're in a terminal state, you'll stay in that same terminal state, like even if there are more than one. And then the reward would always be zero, so you can't get any more reward once you're in the terminal state. So this sort of, even for part two of the book, this is still like how these Markov decision processes are defined. And, the Markov property is that you only need the state action pair to understand what happens. Like there's no additional information. But, there could be like hidden information, which would manifest itself in, different random probabilities here. But yeah, in general, like this function will determine everything. And if the environment is deterministic, that would mean that, all the transitions would have a probability of one, and all you need to do is define like which transition state do you end up in from a given state action pair. And then if the environment is stochastic, it means that from a given state action pair, there could end up being multiple transition states that you end up in. So that's sort of like the setup for all the problems considered in this book. And it turns out like there's a lot of types of problems that can be handled with this type of structure. But the other purpose of this notebook is for me to sort of consolidate all the code I had in other notebooks and sort of redesign certain things and standardize it. So I have, and I try to like add documentation here. And this, you can like see this on the GitHub repository. I'll still be making changes to it over time, but I have here, actually, I'll go down to where the code. So here I have sort of like some base types I've used, but in this case, like a Markov decision process, I sort of have like 3 type parameters here, which are essential for defining it. And that would be like the type, like how are the states represented? How are the actions represented? And then, some numerical type, which will be the reward values that are obtained. So this would apply to any MDP. And then, for this part 1, we're dealing with these tabular MDPs. And in general, for the tabular MDPs, there will be within it like a defined list of states and list of actions. So you could access like the complete list of states and actions. And then further on in the early part of the book, I'm using this term of like a complete MDP, but all that means is that there are some MDPs where we have access to like this full function is available. So that means like there's no mystery. We know exactly what the probabilities are. And in that case, there are certain things we can do that we can't do if we don't have access to this. And I'll come to that later. So for starting out this complete MDP, I sort of have 2 versions of it where there's a deterministic one and a stochastic one. And for the deterministic one, it makes it a little simpler where you can actually just define both like all the transitions in terms of like 2 matrices or one matrix where just the indices would represent like, the XY index would represent just which state action pair you're considering. And then for the state transition map, it just has an integer, which is the index of the state you end up in. And for the reward map, it's just the actual numerical reward, or it also could be just the expected reward. It doesn't actually change the math if there's like a distribution of rewards or a single reward, but this value should represent the expected value of the reward for that state action pair. And then for the stochastic MDP, it's a little more complicated because here I'm just, for simplicity, I'm representing it as a dictionary, but this dictionary will map state action pairs to another dictionary, which will map all of the possible transition states and their associated probability and reward. So it's a little messier, but this way you can, like, if there's a lot of transitions that aren't possible, you don't actually need to include them in the dictionary. It'll just be assumed that if there's some key that doesn't exist, then that probability has 0, or that will have 0 probability of occurring. So this only needs to actually save the non-zero probabilities. So yeah, I can leave this up, but so does this make sense that, like, other than, I mean, this is the part that actually defines the behavior of the MDP, and in this one it would be like these 2 maps, but the part that is constant for both of them is like a list of states and a list of actions, which is sort of the defining feature of the tabular MDP. And then, these are just lookup indices for convenience so that you can, pick a state and then index it easily, and you can easily go back and forth between the state itself and the index of the state. So are there any questions about sort of this, how I'm defining these?
This looks really good to me. Thanks.
Yeah, so far you have the abstract MDP between the complete map and just a regular MDP, which has the transition state and action pairs, and then the complete one has the transition probabilities, which are fully known. Makes sense for those abstracted methods.
So then there's some helper functions here to initialize, a value. Actually, I'll get to this later because I haven't even said what the value function is, but these are just some various helper functions. Okay, so for the purpose of this notebook, just to compare everything on equal footing, I'm just going to use the grid world environment as an example for like all of the techniques in part one. So to give you an idea of like what the grid world is, it's a common example used throughout the book. This here, there's code which helps construct either a deterministic or a stochastic grid world, which, you know, like the states are represented by, you know, the XY coordinate pairs. But the grid world's nice because it's really easy to visualize what's happening. So this is sort of a visual representation of the probability transition function for the grid world. But here, like all the squares represent states. And then the actions here, there's only like 4 actions, which are represented by this arrow. So here I just have it so you can change the action. And then this will end up selecting a different state. So here the state is represented by like the blue box. And then this is showing in this you know, dark, in this bolded border, what the transition state is. So in this case, like we're here, also this is a little confusing, but this here I'm showing, oh yeah. So here I actually constructed 3 different of these grid worlds. So one of them is just a deterministic grid world where it's just plain, and where you, like wherever you choose to move, it just moves in that direction. There's a windy one where there are these, on the bottom here, these like wind values. The wind values just push, like if you attempt to move in a given direction, then the wind will push you up, whatever this integer quantity is. So here, I'll move the state over out of the wind here. So here the wind values are 0. So here it's like if you're in this state, every direction you move, you can see, you know, it just transitions into the adjacent state. And this number here just represents the probability of the transition. Here it's showing, so like moving up, you get a reward of 0 with a probability 1. So these grid worlds are set up so that there's a reward of 1 for reaching the goal. And that's it. That, you know, there's alternative ways to set up the reward, but that's how this one is defined. And then this here is showing, or should be showing, wait, this doesn't seem like, okay, sorry, this was working before. They should be showing the stochastic one. I'm trying to figure out why is this not, maybe, all right, I may have renamed something here. Show, okay, well, I'm not sure why this isn't showing anything differently. This was working a second ago. But in this one, it should show, yeah, what was that?
Oh, I thought that, you know, because of the p-value being 1 or something like that.
Well, no, I mean, this is just showing the exact same thing as the one above it. But what they should be showing is, oh, here, okay, now, wait a second, why did that work? That worked for like a second. Anyway, in this one, it should be showing that the, okay, now it's working for some reason. I'm not sure why it wasn't working before, but this is now showing, so like in this state, if we try to move left here, because in the stochastic grid world, what happens is if there's wind, then oh, I know why it wasn't working. Because yeah, so if there's no wind, it's not stochastic, actually. Everything is deterministic. If there is wind, then you basically have a 1/3 chance of the wind value being, you know, 1 less, whatever it's supposed to be, and 1 greater. So there's like sort of a spread of possible wind values. So now you can see in this, you know, stochastic transition to the left, there's sort of a 1/3 chance of ending up in any one of these squares. And if I make the action right, you can see that. And then if the action is down, It's the same thing because this is pushed up and then, yeah. Yeah, so in this case, because the wind value is 1, there's a chance of the wind being 0, which corresponds to this case. And here you actually only see like the central value being possible. So that is the difference between a stochastic and a deterministic environment. And now this, in this case, is like a physical grid, but in general, like all the concepts of these transitions and the reward, like, if you have a tabular MDP, you have like a long list of states, and here like the states map onto like a two-dimensional grid. But whatever the problem abstractly is representing, you can sort of think of it as a grid world anyway, where there's just like different states that you end up in, but those states may represent like other more abstract things like in a different environment. But it's a good model to use because it's very easy to see what's happening and visualize how the transitions work. So does this make sense to people? It's like visualizing an MDP.
Yeah,
So
the visual for the different states makes sense.
yeah, so here also like because this transition up from here actually goes into the goal, this now has a reward of 1, right? All the other transitions I was showing like have a reward of 0. So going into the goal has a reward of 1. And then here you could see like the reward of 1 is only with 1/3 probability because this is stochastic. And then also because this golden square is the goal state. So because it's the goal, you can't transition out of it. So like you could see any transition, like if I change the action, all of these transitions are going to end up here and there's no reward. And that's true of the stochastic MDP as well. So yeah, this is sort of like the purpose is just to introduce like what is meant by an MDP and the transition function. So seems good. No follow-up questions? Okay. So then what we haven't talked about yet is actually policy. So the policy is actually defines how an agent would behave in an environment. And by the behavior, we really mean the action selection. So this policy function just defines the probability of taking any particular action from a given state. So policies can also be either deterministic or stochastic. If the policy is deterministic, it just means that for every state, there is a single action that is taken with probability 1. And if the policy is stochastic, it just means that you just have to define the probability distribution over actions for a given state. But then once we have the policy function, then we can start talking about trajectories in the environment where you actually select a specific action. And that's where we go back to this diagram here, where there's like a specific list of state action reward values. And like these, this action selection would come from whatever policy is being followed from this state S1. And then the reward would come from the environment. So really like everything else comes from the environment, but the action selection, has to come from the policy function. Is that clear? The what's meant by the policy? And then, in order to actually do this, you have to sample. You have to have some way of sampling actions if the policy is stochastic. If it's deterministic, you don't really have to sample. You just basically look up which action to take. But if it's stochastic and you would like to sample, some trajectory, you have to actually select a specific action. And that's what happens in this function, which runs an episode. So like given one of these MDPs and a policy matrix and some starting state, what this will do is it will continually sample actions in the environment and it will produce transitions. And then in the grid world, that would manifest itself as some sort of path in the environment. So here, again, I'm representing here the policy function with these arrows. So here there's like 4 possible actions. And this shows one way of defining the policy as just a matrix. So here, the rows represent action indices and the columns represent the state indices. There's 70 states, 4 actions. And here I've defined a random policy, which would just have an equal probability of taking every action. So basically, every column of this matrix is a probability distribution over actions. And then here, these arrows just show the sort of the intensity of the color represents the probability on each action. So, right, this representation is equivalent to this. It's just showing it in 2 different ways. And in the grid world, this is what's meant by like the uniformly random policy. And then once we have the random policy, we could, create some trajectory through the environment. So here I'm starting at this starting state, and this is showing a path through the deterministic grid world. So it just wanders around until eventually it reaches the goal, at which point the episode ends. So this is what, visually would represent. But, here I'm showing the run episode called with all the different MDPs I've defined, but they end up just producing the same thing. So here, all this function does is it really produces a list of states, a list of actions, and a list of rewards, which just corresponds to every step of the trajectory. And these are just all the, these are the indices of the states and actions, not, so you would have to, look them up with the list of states and actions. But here, like the terminal state is 60 here. So like this goal is in state 60, but it's physically here on the map. So does this make sense? Like what is meant by an episode and like, producing an episode from a policy. Okay, because then what is like the policy? So like now that we have the idea of actually policy producing a trajectory in the environment, we can get to sort of the actual meat of the book, which is the idea of the value function. So we can define this quantity G, and what this quantity G is a discounted sum of all the future rewards obtained past this point. So, if we actually are, compute an episode or have a trajectory, in the end, like we visited a bunch of states and actions, but ultimately all that matters is just the list of rewards until the end. And the goal of sort of solving these MDPs is to try to maximize this quantity. So the goal is to get, from whatever state you're currently in, is to have the highest sum of future rewards. And the reason why there's this factor gamma to discount it, it's an optional factor. It could just be 1 if the environment is episodic, which means it has a terminal state. The reason why you may need it to be less than 1 is if you're in an environment that doesn't have a terminal state. And in that case, there won't be an end to the episode. It will just be a bunch of transitions that go on forever. And in that case, in order to guarantee that the reward sum converges, this, gamma factor has to be less than 1. But from this definition of G, we can actually write it recursively in terms of G at the next time step. And that this sort of trick is used throughout the book. It's very important in deriving these relationships for the value function. But the first place you see it is really in thinking about the discounted sum of future rewards. So it should be, I mean, this is just a very simple derivation here, but you can see from this definition that once you isolate the sums at the next time step, those just look like the definition of G at the next time step. So you can create this recursive relationship for G. So does that make sense? Because then this directly ties into the definition of the value function. And so the value function is just the expected value of G. And there's two main types of value functions that are discussed in the book. The first is the state value function, and that is defined as the expected value of G given that we're in a specific state at time t. And this is, of course, this expected value, it has to be under a certain policy, right? Because if we don't define the policy, then we have no way of knowing like what this trajectory is going to look like. But the idea is that once we define a policy, then there's some expected value that exists for this, which ends up being controlled by the expected, future actions and state transitions that are encountered. And then the state action value function is very similar. The only difference is that we not only specify the state we're in, but we also specify the action. So, we have a separate value for every action taken, but then future actions taken in the trajectory will be controlled by the policy. But the initial action from state S will always be defined ahead of time in the function. Now, in the book and in previous sessions, we had gone through like deriving these recursive relationships for the value functions, but it always like we start with this definition for both of them. And then I just copied this here from a previous notebook, but you can end up using the definitions and the definition of the expected value and this recursive relationship for G. And by sort of massaging it back and forth, you can end up with two equations, which are the bottom equations here and here. And these equations are recursive relationships for the value function, for the state value function and the state action value function. And here, these recursive style relationships are called the Bellman equations for the value functions. And we can end up, it becomes important that we can actually exploit this relationship to compute the value function if we actually know the probability transition function. So you can see here, like if we have a fully defined policy function and probability transition function, then we have a system of equations for the value function, for both value functions. And in principle, you could solve the system of equations, but it turns out there is a much easier way of solving this, which is covered in the dynamic programming section of the book. And I sort of have a sort of hand-wavy description here of it. But the idea is that if the value function is correct, like if whatever values we have for Q or V satisfy this relationship, like this recursive relationship, then we know that the value function is correct. So like we have a way of verifying the value function is correct. Now, what is less obvious and what is proven in the book is that you can convert this from a check of correctness into an operator that you can apply. So in other words, you can actually go through the state action pairs and you can set this equality at each point, right? So like if you initialize these with random values, let's say, which is commonly done, then we have all these values, right? Like we have all these values and we have all of these values, and these values are not correct, but we have them. And we can basically set this equality, and we can keep going through and setting it, and eventually the process will converge. And once it converges, then we know the value function is correct. Now, it's not exactly obvious why that process should converge, but you can prove that it does. And that is the principle behind the dynamic programming techniques in the book. And the first technique is this policy evaluation, which is that we're given a defined policy and we want to compute the value function for it. And we end up using this sort of like Bellman operator to compute that. Well, I know, but this is sort of like the crux of like chapter 4 in the book. And like I have more detailed proof of this and more elaboration of this in the earlier notebooks, but as sort of a general overview, does this make sense to everyone? I mean, I'll show an example of it next. But yeah, so I read this here. It's like it should be obvious that you can use these to verify you have the correct value function, right? The less obvious part is that you can use this as an operator to update an incorrect value function and progressively make it correct. But that's the idea behind the dynamic programming techniques. So that is what is done in this Bellman policy evaluation, where there are these update functions that will go through. So here it's doing it for the state action value function, but you can also do it for so here it's like, I'm representing the state value function as a vector and the state action value function as a matrix, where again, just like the policy, the state action pairs are represented by the indices of the rows and columns. But you can see inside of this function, this step, and so I mean, I have to accumulate the probabilities if it's a stochastic MDP. Here, this is easier to see for the deterministic MDP, but this update here, like this combination of updates, is just actually evaluating the Bellman operator, where I'm taking the R plus gamma plus V. So here, if you go back up here, if you have the Q function, you have to sort of, this quantity here is equivalent to the value function at state S prime, but here you have to sum over the policy probabilities to get it. And that's what's being done in here. So I'm sort of like, you can always compute V from Q. So that's what's being done here. If you only care about V though, like I have here, then this line here just looks exactly like the Bellman operator for the value function, where we still have to sum over the policy probabilities, but this quantity in here is just the reward from the transition plus the discount factor times the value function estimate at the transition state. And given an MDP, you can, so these functions here are what perform this policy evaluation. There's sort of two convenience functions for it, for Q and for V, like depending on how you initialize the value function, it will control like which version you're doing. So here, like the value estimate is just a list of the estimated values. Whether it's a vector or a matrix will affect which version of the algorithm you're using. But here, so this is showing the impact of computing that on the random, for the random policy. So here, what I'll do is, so this slider bar controls the discount rate. So if I make this 1, so this is like another important point, is that this is the random policy, right? So like it's going to wander around. Eventually, it will reach the goal. But if gamma is 1 for this problem, then what should happen is that all the value estimates are 1. Now, does that make sense to people? So there's a single reward of 1 obtained from transitioning into the goal state. And if there's no discount rate, then right, any trajectory will produce a reward of 1. Like it'll be the single reward whenever it terminates. And because the value functions are the expected value of G, then the correct value for every state is just 1. And this is true. So I have here the deterministic one, the windy one, the stochastic one. They're all the same, right? Because there's no difference. So does that, I hope that makes sense that, yeah, right. If there's no discounting, these all just produce the reward of 1. Now, if I change this, I make this discount rate less than 1, then, well, maybe I'll ask, but like, does people infer like what the value should look like? Again, this is for the random policy. And it's basically each one of these values represents the expected discounted sum of rewards, until the terminal state is reached. So like, depending on the type of grid world it is, if I set this less than 1, the values will certainly change, and they should, be less than 1. But, there's like predictions you could make. Like, for example, if I ask like, well, like the values close to the goal, versus the values far away, like, does it make sense? Or like, is it pretty obvious to people what the values will be like close to the goal versus far away? And how it might change for the windy or the stochastic one?
So I'm going to take a little stab at this. Discount functions represent time. And so a discount function allows you to create essentially a temporal gradient across the possibility space. And if they're at a discount factor of 1, there is no gradient at all. And at 0, there's no gradient at all either.
Yes, I could actually, can I set this as 0? No. I made this so I can't set it as 0. Setting it as 0 is very strange because if you set gamma to 0, then you are sort of saying that, yeah, like the future doesn't exist in the problem.
Yeah.
And that, yeah. But setting it at 1, I mean, another interesting thing about setting this at 1 is that, I mean, if the random policy has a value of 1, I could tell you that any policy should have the same value estimate of 1. That should give you some sense that there is no difference between the policies. Like no policy would be considered better than another one, which in this case might not be what you want. And that's because I've designed this problem where there's just a reward for reaching the goal. So yes, if you set gamma less than 1, it means that the longer the expected time, or the greater number of steps you expect to take before reaching the goal, then that will sort of take the reward of 1 and multiply it by gamma to the n power, where n is the number of steps until you reach the goal. So then if you're starting close to the goal, that should probably have the fewest number of steps expected to reach the goal. And then if you're far away, let's just say, so I'll just set this to like negative 0.99. But here, now you can see that like this state in particular has the highest value estimate. And then these all have the lowest. I'm rounding here, so I'm not showing the exact values, but these are like close enough to being the same. But also, like, does it make sense to people why? I mean, why would this state, for example, have a higher value estimate than this state? Like, is there any
bounded on the right.
Yeah. So like you're sort of like, even though they're each the same distance away from the goal, this has less room to wander far away. And then, yeah, this corner, but again, like this is just for the random policy. So you can also convert this to an estimate of the number of steps, because it should just be like the log, yeah, the log
Yeah.
of this is,
Yeah, so the expected number of steps should be the that value divided by log gamma, right?
mhm.
Or like the log about that value divided by log gamma.
Yeah, I believe that's correct. I mean, we can try it here, but it's like log of, yeah. And if I make, yeah, okay, so 126 steps or something, it seems like quite a lot. If you make the reward -1 on each step without discounting, which is another example in the book, then you can just read directly the number of steps from here, because it'll just add up a reward of -1 for every step. And there was a smaller, that was one of the examples in the book. But now as I lower this discount rate, what happens is all the values, far away get smaller and smaller, because we're doing, we're discounting the reward more, the more time steps in the future. But you could see like whatever discount rate we pick, the relationship between the state value should be the same still. Like this, I mean, it's going to get harder with the rounding, but like this value will like remain the highest value. And now we can see actually that the values in the corners here are lower than the starting value. So here, I'll set this back to like 0.99. But now, so this is showing how many iterations it took for this process to converge. So each iteration is like an entire sweep through the state space here. And here I'm doing this with on my I think I'm just computing the state values here, I believe. Yeah, so I'm doing the V version of policy evaluation, where I'm just using the state values. And you could, so this is showing these are all using the same discount rate. So here, the windy grid world, you could see the values are much lower. And that's because the wind is like high here, and it keeps pushing you away from the goal. And now it should be obvious why this state is now the highest value, because this state is like, and this is actually the highest, because from this state, if you move up, you're guaranteed to end up in the goal. And if you move down, you're also guaranteed to end up in the goal, because there's a wind value of 2 here. So yeah, the wind does dramatically change. Whereas like in the normal grid world, like this is the highest, and then this is lower, and this is lower. And then in the stochastic wind one, weirdly, the value at the starting state is higher than in the non-stochastic wind one. And that's probably because you have some easier time of accidentally ending up in the goal here, because the wind values might be 0 or 1. Whereas here, like you always experience a wind value of 2 here. So like there's a lot of actions you can take to just where you overshoot the goal. But you can also get a sort of idea of the strategy to employ with wind. But here, like notice, like this corner is sort of a good place to be with wind for both of these, versus like this corner is really bad. So might give you a hint that like there might be some situation where we want to end up down here before trying to wrap around it and get to the goal. So yeah, but this is just sort of proving that if this converges, the nice thing is you've sort of proven that you have the correct value function, because the correct value function has that property. And like I said, you can verify the value function is correct, right? By verifying this relationship. And that's what's being done there. So that is yeah, just policy evaluation. And then the next sort of question becomes, why, like, what's the purpose of computing the value function? And, there are sort of two perspectives on this. The first one is that there is a new set of Bellman equations that we can define, which are called the Bellman optimality equations. And I'm not like proving it here, but the difference between these and the other Bellman equations is that there's no policy anymore. So here, if you compare the two equations, this max operator is replacing the policy completely. So this, in the previous section, was a sum over the policy distribution, and now we're replacing it with the max. And this is actually this is easier to derive using the state action value function here. But the idea is that there exists some optimal value function, which is the meaning is that at any given state, under this policy, there is some reward value, some G value that you can achieve. And there is no other policy that will produce a higher G value. And the definition of it is really simple in the case of the state action value function, which is just saying that this optimal state action value function is defined as the maximum value that you could see for under any policy. Oh, I'm sorry. Actually, that definition is actually the same for both V and Q, but you end up using that to derive this recursive relationship again in the form of the Bellman equation. And actually, the sort of first stepping stone to deriving that is by considering the optimal state action value in its relationship to the optimal state value. So, I mean, this is sort of a logical argument that the optimal state action value, the optimal state value should equal the maximum state action value at that state where you maximize over actions, right? So we actually have the values here, the optimal values for every action, but then one of those actions will have the highest value or will be tied with others for the highest value. And this state value should exactly equal that. And then just like in the derivation of the Bellman equations, I found it sort of easiest to see how the relationships work by going back and forth between Q and V. But you can sort of then re-express this in terms of the state value function, right, with the recursive relationship for the state value function. And same with this step, but what you end up with is that the policy, what was previously a sum over the policy distribution, is replaced with the maximization over actions. So again, we can verify that a value function is optimal by checking if this is true. And it turns out in the same way we can turn this into an operator, it's also possible to turn this relationship into an operator and just directly compute the optimal action value function. But before doing that, actually what's done in the book is going over the idea of policy improvement, which is the idea of not really using this directly, but rather computing a policy function. Here, like we have, let's say, the Q function, and then changing the policy in some way that is guaranteed to produce a higher value. And again, like the insight into doing this comes from the Q function, because the idea is that, if we start with a given policy, pi, and we have the Q values, we can look at the Q values and we can say, well, what if at a particular state we identify an action that produces a higher value than this V, right? So like that would mean that the policy that we are starting with isn't actually taking that action, right? Because like if it was, then the V would match that. So we can look at all the Q values. We can sort of define a new policy that has this property. And the property is that like at a given state, we consider the action that policy would take. And we observe that that Q value is higher than the value estimate for that policy. Then this is what is, in the past we had proven this, but the idea is that if this is true, then that implies that actually the value function of the new policy at that state is guaranteed to be at least as good or better than the old, than the value function under the old policy. So like this implication is what the policy improvement theorem proves to be correct. And like the reason why it's not like you can't just go directly from this to this, because once we change the policy, like if we select a new action at this state, then we're also going to possibly change the values at all of the other states. So like, sort of the magic of the policy improvement theorem is changing this pi in the V into the pi prime, where we're actually, working in terms of the value estimates for this new policy. Because this is just making the statement that if we select the better action once, then like that will be a better action to take. But then we have to continue to follow the old policy after that, because those are the value estimates we actually know at this point. But you can prove by expanding all this stuff recursively, kind of like we did before, that this in fact will produce a policy which has, better estimates overall, higher value estimates overall. So this also gives us a method of producing the better policy, which is that we just look at the state action value function for a given policy. And then we go through and at every state, we just set our new policy to be the action that maximizes the state action value. And you can compute. So if we have Q, you can just directly look at this and find it. If we only have V, then it's a little harder because we have to sort of use the probability transition function to compute Q from V. And so this top line would show you, how to do policy improvement if you have the Q function. This shows you how you have to do it if you have the state value function, which is fine as long as we have this probability transition function. If we don't have this function, then this is the reason why for future techniques, we usually try to compute this function instead of this function. But in the case of having, these complete MDPs with the full transition function, we can do policy iteration with this, even with the state value function. So all you have to do is define this way of like so defining this, because this is we're taking the argmax here. This is called, making the policy greedy with respect to the value function. So both of these, are the action of making it greedy because we're selecting what appears to be the best action or the greedy action. So performing this update is what is known as sort of a step of policy improvement. And then, sorry, if I okay, so I guess I don't have like a diagram here. It's in the book, but the idea is that you improve the policy, then you recompute the value function for the new policy, and then you just repeat this process until you don't observe any improvement. So basically the optimal policy is a fixed point of this process. But if I show you the code for policy iteration, what it does is we start out with a random policy. We evaluate the policy to get the value function. And then we make the policy greedy with respect to the value function, and then repeat that process over and over. And then we check if the policy has stopped changing. And if it stopped changing, then that is guaranteed to be the greedy policy, as long as these value estimates are actually correct. But remember, we're using the Bellman policy evaluation. So we also have a way of verifying that the value function is correct here. So to see this in action, I've set up the same grid world here. And actually here, there was a question before of whether the discount rate can actually change what the optimal policy is. And in general, it can. And one of the easiest ways to see that is with this example. So here, I've created this grid world, but now there's like a secondary goal up here. And this is just the deterministic grid. Oh, actually, here, I'll make this deterministic. So this is just the plain deterministic grid world. And now there's a secondary goal with, here, I'll make the reward here. So if I make this like here, so now there's a secondary goal with a reward of 0.5. So remember, like this goal has a reward of 1, and this goal has a reward of 0.5. So it's a lower value. Now, what happens is, depending on the discount rate, it actually will make sense to pursue this goal. So here, I'll change this value here. So like, let's say if I set this discount rate like to 0.8, so now I'm like discounting future rewards a lot more. Now you can see that along this side and like out to here, there are these states where the optimal policy is actually to go to this goal. Whereas like once you're here, the optimal policy is to go to the original goal. And the reason is that even though this reward is half of this reward, if the discounting is high enough, the faster time reaching this goal will make it more advantageous. So if I put this back up to like 0.99, then you'll see that in like every situation, it's better to head for this goal instead of that one. So what this is showing, the policy iteration process. So what this is showing is that after 0 iterations, so wait, is this actually yeah, so this is showing like what the function looks like after different numbers of iterations. So this converged in four iterations to the optimal policy. Actually, this starting point shouldn't be, I think maybe I'm starting with something initialized. Well, it should be initialized randomly, but this is basically showing what the value estimates look like. I'm sorry, this policy represents, oh, I know, maybe because it already, yeah, so I believe this is already like the optimal policy, at least for these settings. And that's because I think for this simple grid world problem, once you evaluate the random policy, then the greedy policy with respect to the random policy is already the optimal policy. So I think.
So policy after iteration 0 is, there's one iteration of policy, right? So the policy after iteration 0, if it starts with a random policy, seems like it would be random policy.
Yeah, so it should be, yeah, but I think I'm basically showing this is sort of like iteration 1.
Sort of a off by 1 thing.
I put in, oh no, it should start out with the random policy. Yeah, well now I'm not sure. Yeah, because the history of this should be Yeah, I mean, it should start with the random policy, and then this should be like the value function for the random policy. But forget iteration 0. I'm not sure what the problem is, but if this is iteration 1, this would be the greedy policy with respect to the value function for the random policy, right? And now this is the value function for this policy, right? So the idea is now that we have this value function, now we can look at this value function and update the policy. So like, for example, here from this state, the obvious like best action is to go to the right because this state has a higher value estimate than this one. And if I step this forward to 2, you see now this policy has been updated to go to the right. And this is already like pretty close to optimal. You could see it might make sense that early on in the process, it's confused and thinking that it's actually good to go to this state. And it takes a few more iterations to realize that actually it's more advantageous to go all the way over to this state, at least with this discount rate. But anyway, at the end of the process, this is showing the optimal policy. And this, like, it should be kind of obvious, like, why this is the optimal policy. Like, we're just moving, like, directly towards this goal. And in all these other states, other than the ones aligned here, you could see how there's actually 2 optimal actions because going in either of these 2 directions is, like, equally optimal. Because, you know, we have to go. We can only move, like, rectilinear style anyway. Yeah. So, but the point of like this example is sort of like to show how if I lower the discount rate, then so this is the first. Wait, maybe I have to see when the first time is. Yeah, so at 0.92, it's still there's no change to the optimal policy, and then now at this discount rate, at least with this, you know, secondary goal reward. Now we could for the first time, see a slight change to the optimal policy, where if we're 1 step away from this goal, the expected time it would take to reach this goal now makes this reward worse than this one. Now, this is like a really contrived, like toy example of this, but the concept is the same for any MDP. So like if you have a problem where there are possibly different like goal endpoints, then the discount rate may actually change the optimal policy, which is like could be really bad because you may not know like what discount rate is actually important for the problem. And you are effectively like putting a value difference between like the time, like the relative time to reach rewards. But I could give there's one example of this I could bring up, which is like if you have a game like tic-tac-toe or something, and you say there's a reward of 1 for winning and a reward of like -1 for losing. Like let's just say. Now, if you don't apply discounting and you try to solve that MDP, you will get a policy that is optimal and will win, but it is indifferent to the length of the game. So like if you're looking at candidate moves, you know, or if a game is going to end in a draw or a win, it will never prefer the move that like wins immediately. Like if there's an immediate win, but a guaranteed win in future steps, then it won't prefer the move that does the immediate win. Now, you could fix that by using a discount rate, like some like 0.99. But as soon as you do that, you're actually creating a situation where a loss could be acceptable, like as long as the relative probability of the loss is overwhelmed by like the speed of victory. So like there is a certain probability and speed of victory that would actually make up for a slim probability of losing, right? Because like you have this situation where there's like an outcome that's worse and an outcome that's better. And, you know, if there's some policy that leads to the good outcome fast enough or faster than an alternative policy, then it may prefer that even if it opens up the possibility for a bad outcome. So you're sort of putting a relative weight on how much you care about bad outcomes, like as long as you reach good outcomes faster, more frequently. And sometimes it's really not obvious like what that balance should be. Like if you're making like a tic-tac-toe agent, I would imagine like most people would probably consider a loss to be totally unacceptable. But you also can't like set the reward for a loss to be negative infinity, because then you don't have like, actually, I don't think you could do that anyway. I haven't thought of that, but it seems like that's not something that would work. I mean, I guess, because then your values are no longer converging. As long as you avoid the loss, the values converge. But when you're actually, as you're computing it, you may not be able to avoid those infinite values. So I think like this sort of general balance and choosing the discount rate is like pretty important for certain problems. But I believe like that's why if you're training an agent to like win at a game, I mean, usually people avoid using a discount rate. Because like if you avoid a discount rate, then you're simply just saying like, like you're just maximizing the probability of winning, and the speed is like taken out as a factor. Although I think in the tic-tac-toe example I used, I believe like even setting the win at 1 and the loss at -1, it still can affect the optimal policy, because like that still puts a relative balance on how good winning is and how bad losing is. Like this wouldn't happen in tic-tac-toe, but in a different game, like if there was some policy that, lost some small percentage. I mean, I guess if they're weighted equally, it should still maximize the probability of winning. But you basically want to construct the rewards so that the probability of winning is maximized, as opposed to like the probability of winning, quickly, which may actually cause losses that could be avoided.
Well, there's also cats, right, which complicates the case for tic-tac-toe, right? So if the relative balance of the reward for winning and losing actually matters because of cats, right? So if you, for instance, have a higher negative reward than for losing than a positive reward for winning, the policy will essentially, well, I mean, it will likely guarantee a cats, right? Or I mean, I guess it also depends on the
But
relative.
you mean a draw?
Yeah, sorry.
Yeah. So you could also make the reward for a draw 0.
Right.
But then if you make the reward for a draw like -0.5 or 0.5, right, that will actually affect the optimal policy too.
Right.
Because it's like, what is it going to optimize? Like the relative, because you sort of have to think about like, you're basically summing up the expected probability of winning, drawing, or losing. And if there's a balance between, like, you could achieve the same like expected value of reward with different combinations. Like if you win a certain amount and draw a certain amount, but then like drawing that amount is equivalent to like winning more, but also opening up the possibility of losing like a smaller percentage than the draw percentage. So yeah, I think like in that case, especially if you have wins, losses, and draws, even just your selection of those rewards will affect the optimal policy. Because you're sort of like need to define what you mean by like a good policy. And actually, because I was trying to I was creating an example of this for Wordle as well. And if you're thinking about that game, like the game is pretty easy to win within like 6 turns. Just if people, I assume like most people are familiar with Wordle, but you just make guesses and you're trying to guess the correct word. You get information for every guess you make. But if you're trying to like optimize it, you have to define like what you mean by like scoring the game. Even if you're like conducting a tournament and it's like you could score someone by like giving them credit for finishing the game faster, like score in fewer turns, but then you still have to consider how to handle what if someone loses the game, like because if you give someone like a score of -1 for every turn they take, so like if you win in 1 turn, it's like -1. If you win in 6 turns, it's -6. So there's like a relative, it's like 6 times better to win in your first guess than on the 6th guess. But then if you lose, well, you could score the loss as like -7, I guess. But that's also equivalent to like if someone had won the game in 7 guesses, but like they might have lost the game in 7 guesses. So, that choice of like how badly do you weight losses will like dramatically affect what kind of policy. Because like you in Wordle, you could easily imagine a situation where you could have a policy that wins quickly much more frequently, but has like a 1 or like a 2% chance of just completely losing, versus another policy may like be guaranteed to win in 4 steps or something and never lose. And depending on how you're scoring the game, it will affect which thing you prefer. So at some point, it becomes like a sort of philosophical choice of like, what do you mean by doing well in this game? Like you actually have to define like precisely, like, yeah, what it means to have a good game. But anyway, this process in dynamic programming, this is like the policy iteration process where we, continually find the value function and then make the greedy policy. What is probably in some ways easier to see just from the Bellman optimality equations is this alternative called value iteration, where you just turn the Bellman optimality equation into an update rule, just like we did before with policy evaluation. And this completely dispenses with policy improvement. We never actually consider any policy in this. And it turns out that applying this process with some randomly initialized value function will also converge. And once it converges, we're guaranteed to have the optimal state value function. So that is the, value iteration. And you could see this is applying it on the same grid world, but you could see it just arrives at the same optimal policy as the other one. And if we like change gamma again, it's going to do the same thing where it starts to favor going to this goal instead of this one if gamma gets lower. But the idea is like those are the 2 extreme cases of this. In general, this idea of generalized policy iteration is that we could partially compute the value function and then make a greedy policy with respect to that, and then partially evaluate it again. And whereas like in the case of value iteration, we never even, our value function isn't actually converged to the correct value until this whole process is finished. So along the way, we never had, so we never had any intermediate policy or correct value function. Whereas in the case of the policy iteration we had before, wherever it was, at every one of those steps, we had like a fully computed value function and policy. Like each one of these steps, like this value function is the correct value function for this policy, but yet neither one of them are optimal yet. In this case, we just, at the end of the process, we have the optimal value function. And this idea of generalized policy iteration comes up in the next sections on sampling, where we sort of have some point at which we decide to stop improving the value estimate, and we just update the policy. And that sort of deciding to stop before we're done converging is the general part of this, where we don't have to take either extreme in the process. But the sort of the final part of part one handles the case where we don't have the probability transition function. And in that case, what we have is the ability to observe transitions. So that means like we have a state action pair and we can observe a reward and a state transition from that. If the policy is deterministic, then this will always be the same outcome. If it's stochastic, then we could observe different values of this. And, you know, in chapter 8, actually, one approach you could take is, instead of like what we do with these sampling techniques, is you could try to like build a probability transition function from these observed samples and then learn off of that. And that would be like the sort of modeling case. But the most direct thing that you can do is just to try to directly apply some of these techniques from the samples themselves. And these techniques are really easy to understand, because if you start with the definition of both value functions here, which is just the expected value of G, right? And the expected value of G is just the expected value of this sum of the rewards, either starting from a state or starting from a state action pair. If we sample this trajectory from the environment, then we have a list of rewards and we can sum it up. And that sum is actually just an unbiased estimate of this. So the idea behind Monte Carlo sampling is that we just estimate the value function like with its definition, basically. And this diagram here is showing like when you have this trajectory, you start from a state. This little pi above the arrow means that we use a policy to produce an action. And then the second arrow is that from that action, we use the environment to produce this transition. And we just repeat that until we hit a terminal state. Right? So then we just extract from this all the reward values. And then at any t, we can just sum up all the rewards from t, you know, going forward. And then we directly have our estimate, our value estimate. So now in order to do this, we need a new type of MDP. And here is where I'm sort of calling these sample MDPs instead of the other one. So in the sample MDP, we no longer have the probability transition function. Instead, what we have is a step function. And what the step function does is it produces this tuple, you know, it basically gives us this step here. So we give it a state action pair, it gives us the reward and the transition state. In addition, for these functions, because we are going to be running episodes like this, we need some way to initialize the episode. So by convention, I'm just saying there's some sort of initialization function that produces a starting state. And there's also a function that allows us to check if a given state is a terminal state. And then we can, you know, end the episode. So yeah, these types end up implementing this, but the important part of these is really the step function. Like that's the key to what makes these MDPs different than the other one. And also, you can always convert from one of the previously defined MDPs to this type, right? So like if I have the probability transition function, I can always like convert it into a step function. So that's what, there's a function here that does that. So you can like convert one of these stochastic MDPs or deterministic MDPs. Actually, where is the, yeah, deterministic MDPs into one of these sample ones. So that's what's done here. So I could just make 3 new versions of the grid worlds I had, where now these grid worlds are the sample style grid world. So all I can do is take steps in them. I can't observe that full transition function. And then I have like a way of creating an episode from these with the step function. So to make an episode, I just take steps, keep track of the rewards, and then the end of the episode will produce this list of states, actions, rewards, and then the terminal state as well. And then, the Monte Carlo prediction algorithm is really simple because all we have to do is average the rewards. Like we're just, directly averaging this, where we're just collecting the rewards from the trajectory. And every time we visit a state, we have some example of a trajectory, and that will produce a G value. So that's what happens in Monte Carlo prediction. And here we're just doing a simple average where we keep every time we encounter a state, we just add it to, we compute a new sample G value and then add it. But here, this is showing for all of those converted. So I've like taken the other MDP and converted it. And this is, again, the random policy. And this is just showing that if you apply the Monte Carlo prediction, because I already have the reference values. So the reference values are like from the Bellman policy evaluation from before. And this is just showing that the more episodes you collect, the lower the error is with the reference value. And yeah, these, I think, yeah, these values were all initialized at 0. So that's why these start with a lower error, because the windy grid world has lower value estimates at closer to 0. So the value starts with lower error. You could see it converges like these methods. You could see here that the deterministic grid world actually seems to like be converging faster than the others. And that should make sense because the samples from the deterministic grid world are better. It doesn't explain why. I mean, the windy one is also deterministic, but I'm not actually sure why this is converging slower, but it's probably just, a property of the MDP. And these are really simple examples. You could see, like, depending on the MDP, like, this process may not converge very quickly or well, depending on how complicated the MDP is, or, how well the trajectories actually represent what is happening. I saw, well, okay, so let's see, yeah. So here, because I've already computed the actual values, I can just actually plot this error. Oh, I think you asked, how is the wind implemented? That it's just, I mean, there's just like, you mean in the case of the probability transition function or in the case of the step? Because like all it does is just, if you try to move in a given direction and there's wind, it just adds to the Y value of where you end up. And then it sort of clamps it to make sure you don't, exit the grid world. But yeah. So, I mean, that's just using the Monte Carlo sampling to evaluate a given policy. In the case of finding the optimal policy, we're actually just going to do the same thing again of this sort of generalized policy iteration where we start with a policy, we use the Monte Carlo sampling to estimate the value function for the policy, and then we just update the policy with policy improvement, just like before. The main difference here is that because of the reasons I said earlier, we're going to estimate the Q, so the state action value, because that's going to be a lot easier to update the policy. We don't have to know anything about the environment. All we need to know is Q to do that, the greedy update for the policy. And actually, do I have it up? Well, yeah. I mean, the policy update is just computing the greedy policy with respect to Q. And yeah, so the other thing, so like we have some, we're going to initialize the policy randomly. We're going to, and here unlike in the previous example, we have this sort of natural stopping point for doing policy evaluation. So here you could see that the more episodes we learn for, the better the value estimate is, right? So we could like perform this until it converges and then update the policy. But we don't actually need to wait for this to converge. We can already start improving the policy, even just having partially computed value estimates. And the simplest way to do it is actually to just alternate every single episode. So here I collect data from one episode and then I perform the update for that episode where I update the value function and then I update the policy for all of the states visited. And in this case, like the policy update is just by default, it is going to be the make the policy greedy. Now there is another little wrinkle for this Monte Carlo control, and that's in order for this to converge, we have to have value estimates everywhere. And as we get closer to the optimal policy, that policy in general won't visit all the state action pairs, which means that we'll never have a good estimate for any of the values because we may need to know the adjacent values, like all the values end up depending on each other. So one way of dealing with this is just to guarantee that we visit all of the state action pairs, like we have some chance of visiting all of them. And exploring starts does that by initializing the episode with a random state action pair. And that's what's done here. So like there's some method to initialize the episode. And here it's just selecting a random state action pair. So by doing that, it means that if we run this for an arbitrarily high number of episodes, we will eventually be able to, have data for every state action pair. Yes, the notebook, I mean, this notebook and all the other notebooks are available. Here, let's see. It should be, so the meeting link should have a link to this repository. But this repository has this. So these were like the things that previous meetings we covered are these notebooks for the other chapters. And this one is in this, so this is actually on the dev branch of this. Sorry, I haven't like finished everything. But in the dev branch, there is this tabular method summary folder, and that's what has this notebook in it. Yeah. So, but the exploring starts method is the one where we are like the policy we're being updated will approach the greedy policy, which we know, like for this example, the greedy policy is just going to like, beeline it straight for the goal. So, if we start here every time, well, like we're never going to visit these other states. So exploring starts allows us to visit the other states. And then this is also showing, because I know the optimal value function for this as well. So this is showing how this process is converging to the optimal value function. Now you can see, unlike the other method, like this is the optimal value function, like from here, going right is the optimal action. But if you recall from earlier, like going down here is also optimal. So the difference here is like this method isn't as precise. So you're not guaranteed to get that same like precision of knowing that like right and up are identically good. Here, like if you have some slight numerical error in your estimate, here it's going to show like it's only like the value estimate for going up here is higher than the value estimate for going, or like here, than for going right, even though going right here is like equally optimal. You can see like some of the states it shows it. And here, like these value, like this policy is correct. But yeah, so, and this, yeah, this is the one also without the secondary goal. Yeah. So anyway, this is what the optimal policy looks like with this Monte Carlo learning. You see, it's like not as clean as the other method, but it is still converging to zero error over time. And this ran for, this actually ran for quite a few, 10,000 steps. Okay, well, now I'm not sure if the steps refer to the steps. So you can either do it for number of episodes or number of steps. I think I did this. Well, oh no, sorry. This is episodes. Okay, yeah. So that's actually a lot. Max steps. Well, I'm not sure, but you could say it can end up taking a lot of samples to converge, even for a very simple example like this. The other possibility of guaranteeing this exploration of all the state action pairs is to use epsilon soft policies. And in epsilon soft policies, we just reserve a probability epsilon of taking random actions. And this is another way of guaranteeing that we will eventually visit all the state action pairs. However, so here, like it doesn't seem to have affected the optimal policy. It will definitely affect the value estimates though, because here you can see the error here is much higher, even though this, well, actually, yeah, this policy also in places isn't optimal, like here, even though I've run it. Maybe I didn't run it for as many episodes. Or it's just, it might be plotting it differently. Next steps 10,000. Okay, I will look. Oh, I see. No, I think I am still. Well, it should be running it for 10,000 episodes. Maybe because this. Oh, I think this max step is actually for a single episode. How many steps? It cuts the process off at. So this is, oh, I see. This is exploring starts. This is epsilon soft. So I did run this for fewer episodes. Okay, I'll run this for 10,000. Okay. So now it's gonna, but you could see even after 10,000 episodes, this value error is still high, and that's because here I've set an epsilon, a pretty high one, because this actually is good for making sure it explores everything for this size MVP. And you can see that this is actually going to converge to the value function for the epsilon, the optimal epsilon greedy policy. Because of the way this is computed, the policy I'm updating is this epsilon greedy policy with epsilon of 0.5. And that's the data it's collecting. So that is also means that these value estimates are going to correspond to the epsilon greedy policy. It turns out the greedy policy with respect to that value function is still probably optimal, which is convenient. But in general, that is a limitation of this method, that you're only going to find the optimal policy with under the constraint of taking random actions like this. And that, matters for some of the examples later in the book. You can see now this value estimate of 0.19 is much lower than this value estimate of 0.46, right? Because like this is computing it for the greedy policy, and this is computing it for a policy where there is some random actions taken. So neither method is really completely perfect. Like this may be really inefficient because we're just starting in random spots. And this one, we're constrained by this epsilon value. I can also show, I can lower this to a much smaller value, like 0.01. So there's only a 1% chance of taking random actions. And you can see we can converge, but this is actually even worse now because the epsilon's so small that it's not exploring enough. And now the policy is not even close to optimal. So just more levers you have to pull and keep track of. And if you pick the wrong epsilon, it may lead to a bad outcome. This is at least finding the right policy along this path, but the error is still much higher than for this method. And then there's this, I think important sampling. So off-policy learning is a different way of doing this, which I don't really have to cover this now. But the idea is that you can follow a behavior policy and you can have a target policy, which in our case would be like the optimal policy. And then in that case, you can use the behavior policy to guarantee exploration. but you can still compute the value function for the target policy. But you have to correct, there are these importance sampling weights you have to apply to the data, because you have to basically look at the relative probability of a trajectory occurring under the target policy compared to the behavior policy. So there's a bunch of annoying details in this. This is showing for the policy that just goes right. This is using the random policy to collect data, but then trying to compute the value estimates of the target policy. And this is with a gamma of 1. So of course the target policy should just, the value should just be 1 here. And this is showing how, depending on how you do the different weighting methods, ways of using importance sampling, how long it takes to converge. But so like this value is 1, which is correct after, like this is only after 100 episodes. But you can see like as I move, so this is showing like how the value, this is for different runs as well. But you can see like the further I step away, like these value estimates are not correct. Like these values should be 1. And that's because you just need way more data before these value estimates are correct. And the closer you are to the goal, it converges faster because like the trajectories are shorter. So the random policy is gonna, like the longer the trajectories to the goal, the more difference there is between the behavior policy and the target policy. And that means this importance sampling weights get larger and you get much higher variance in the estimate, and it takes longer to converge. But anyway, this, if you want to know more details about this, you can look at the full notebook on Monte Carlo methods, but it covers importance sampling and then off policy control. But sort of the final like important piece from part 1 is this idea of temporal difference learning, and the sort of both temporal difference learning and Monte Carlo learning use samples. And in the case of Monte Carlo learning, we had these samples of the rewards. And that came from the definition of the value function. Now we had this other definition of the value function, or this other equation for the value function, which was the Bellman equation, right? So like this is the Bellman equation for the state values and for the state action values. And you can also write this in terms of an expected value here. So you notice both of these expected values look like things that we can sample from as well. So, but now what we need to sample is a little different. Like here we can see we need one reward example, and then we need some existing value estimate at the transition state. Now we could get this from a trajectory too, and actually this is what it would look like. So we would have a state at time t. We could sample an action from a policy, get R and the next state, and then we can sample the action from the next state. And normally we would go on, in Monte Carlo learning, we would go on for a long distance. But if we are using this form of the value estimate equation, we don't actually need more than this, which means that we can already start to compute updates to the value function just from this amount of trajectory. And you can see here this like state action, reward, state action. This is where this acronym SARSA comes from, where, you know, if you see this like spells out SARSA, but it just refers to this piece of the trajectory that we need to perform this update. But the idea is the same as Monte Carlo, is that we're going to have some trajectory. We're going to take this piece of it and we're going to apply this update. We're going to evaluate this quantity using some existing value estimate that we have. And over time, this, just like with dynamic programming, this is going to converge to the correct value function for this policy. So here we just need to take a step. Like once we take a single step, we can then evaluate. I mean, we do need to initialize the value estimate with something here, and then that will be updated over time. But this sort of step process where we collect this data, we then use it to perform the update. And that's, you can do it just like with Monte Carlo for policy evaluation. And this is showing that same evaluation for both the state value and the action value function. Yeah, this is showing, I don't have a, I'll add to this a plot over time of like the error over time. But you know, these at least are running without crashing. But then SARSA, the idea with SARSA is to then do the same exact policy improvement, which is sort of, we're going to do it akin to the, you know, policy iteration that we had, except we can actually update the value function every single step. So like every time we take a step, sorry, and obtain this, we can perform one of these updates. So now we're doing like generalized policy iteration, but we can actually update the value function and the policy every single step of data that we collect. So like as soon as we do one of these steps, we'll update QSA. And then from that, we can recompute the optimal policy at state S using the updated state action values. And that's what happens in SARSA. And this is showing the effect of running SARSA on the grid world. And also for 10,000 episodes, oh, sorry, this is not showing the error, but rather the number of steps. But you can see this is also converging, it seems like pretty accurately, other than those numerical errors, to the optimal value function. Depends on the discount rate also. And yeah, also this SARSA is using epsilon. So again, a limitation of SARSA, just like with the Monte Carlo control, is that we are still using this single policy to collect data, and we still have to visit all the state action pairs. So in order to guarantee that here, by default, SARSA will use the epsilon greedy policy to update, because that will guarantee visiting all the state action pairs. Now, there is an alternative to this, which isn't as messy as the off-policy learning, even though this is technically an off-policy method. And that is, we can do something called expected SARSA. And the idea behind expected SARSA, if you go back to this equation, is that like, this is the expression for SARSA. And we can see here, there's sort of like two expected values here that are combined. So one is the expected reward, which here, actually, this doesn't depend on the policy. This just depends on the state action pair. And then there's this, right? And this comes from this sum. And you can see how this is the expected value under the policy of Q at the next state. And there's two ways of using this. One way is to just sample an action from the policy and use that value. The other way is to use the policy distribution itself to compute this expected value, since we have all the Q values. And using that is what's known as expected SARSA. And notice that if we're doing expected SARSA, since we've already specified the state action pair, this sum could actually be like the optimal, like we could be trying to compute the optimal policy with this, because, you know, regardless of whatever action we take in the future, this Q update will converge to the Q value for whatever policy we're using inside of this sum. So that's the idea behind Q learning and expected SARSA, where we can actually take trajectories from some arbitrary policy right? Because like all we need, I mean, so we do need to sample the different state action pairs. We'll sample the state action pairs. And we'll actually take this action. But then that action, once we've selected it, is detached from the policy, right? Like it's an input to the Q function. So the policy in this sum here, we can compute it, even if in reality, when we get to the next step, we actually take a different action. And if you look at like this trajectory, like here, we're showing that we use the policy to compute A1. In expected SARSA, we just look at this state and we sort of do a hypothetical evaluation of the Q by not actually taking a specific action, but summing over the actions. And they have the same expected value, but in one case we're just sampling and the other we're computing it explicitly. But the advantage of computing it explicitly is that we can do something called Q learning, where, so when we do Q learning, so the way I've set this up is I just have one function that does expected SARSA. And in expected SARSA, you have the freedom of having also a target and behavior policy. Now, the behavior policy is always being used to actually sample the actions. And that should be epsilon greedy, or it could even be the random policy, because we have to guarantee we visit all the state action pairs. But for the update, I'm not actually using, like, whatever the behavior policy does when it selects the next action, I'm not using it for the update. I am using all of the actions and I'm using the target policy distribution. And then the Q function here is going to be based on the target policy. And then for convenience, for making sure that we're taking efficient trajectories, I can also update the behavior policy based on the optimal policy Q function. But the behavior policy update could be like epsilon greedy, whereas the target policy I'm tracking can always be based on the greedy update. And in that way, this is sort of a way to do off-policy learning without actually needing importance sampling. We don't need the importance sampling because the form of the update we're using doesn't actually care about what the behavior policy is. So Q learning is just expected SARSA, but where the behavior policy is following the epsilon greedy policy, and the target policy is the greedy policy. And then if you leave both to be the same, so there's just the behavior and target policy are updated as the same, that would be the normal expected SARSA, where it's just like normal SARSA, but it has lower variance in its updates. But this is showing, so applying this as Q learning instead of the expected SARSA without Q learning. And here, even though, well, there is a problem here with the policy, but now these value estimates will actually be the value estimates for the optimal policy. And we don't actually need, now the epsilon is not at all affecting the value estimates anymore. And we don't, so this is like a nice compromise where we don't have to worry about exploring starts or being forced to just know the optimal epsilon greedy policy. And oh yeah, I'll have to add an error curve plot to this. This is another sort of interesting point in the chapter. There's a lot more detail on this in the chapter on TD learning, but double learning is just an enhancement of this where we try to avoid maximization bias. I won't go into it now because it's kind of complicated, but if you look at the notebook, also, if you go to this repository, there's a web page here, which has static exports of a lot of these notebooks, at least the ones I've done so far. And chapter 6 on temporal difference learning. This is the chapter that has this explanation of double Q-learning and double SARSA. It's in the section 6.7. So you could read this. I won't, it's going to be too much detail to cover now, but this has an explanation of why keeping a single estimate from the samples leads to maximization bias, which can make it take a lot longer to learn the correct values. And with double learning, you can avoid that. But it ends up conceptually being the same as expected SARSA and SARSA. It's just that it has a little trick to help it converge faster in the case where you have an environment with, especially an environment with high variance in the rewards. Have it here. Yeah, but I think in terms of like the main points of the chapter 1, I think like these algorithms basically cover everything, and the crux of it is really going back to these definitions. So it's like we define the value functions, and for a policy, and we can either use this and try to do policy improvement. And the way we compute the value estimates is either, directly using, this equation or this equation if we actually have this information, or with samples, we can either sample G with the reward trajectory, or we can use something a little more in between where we have this like the bootstrap sample, but we actually, take a sample from a trajectory. And that's sort of the key distinction between the Monte Carlo methods and the TD methods. But both methods end up trying to compute the value function and then doing policy improvement off of it. And then the dynamic programming, the Bellman update equations are, the purest form of the update that are able to make full use of the probability transition function. And they also will give the most precise answers. That's what here, like they'll give the most precise answers here where there's like no numerical issue, no sampling error. But you also need to have access to the probability transition function to use these techniques. Whereas if you have the step function, for sampling, then, we can either use it for Monte Carlo sampling or we can use it for TD learning, where we use this other form of the update. But all the techniques are just sort of slight variations to the, the generalized policy iteration concept. But I also set this up so this was planning on adding a package in here that could be used like outside of the notebooks, but in here I haven't like finished updating it yet. But the idea is like this package will just actually import this notebook, and then it can like be used in like normal code. Because the way I've written this isn't true of the other notebooks, but the way I've written this notebook is like all of these examples here don't actually run when you import it like as code. And the only thing that will run are like the function definitions and the type definitions. So hopefully when I am finished with this, it should have like a comprehensive set of all of the different like relevant techniques in part 1. But I'm not quite done yet. Let's see here, I finished with at least the TD methods, and then I'll probably add a few more techniques from the planning and learning section, and probably something for after states, which I haven't added yet. But I may also still make some design changes to the the types and functions. If anyone has any feedback on how to structure this too, you can let me know. This code like will look different from the code in the other notebooks because I'm still sort of like, I was sort of in the process of redesigning things and making the naming conventions better and sort of, now that I've gone through all the code, I think I have a better way of organizing it. But yeah, once I sort of finalize everything, it's going to be harder to change. I mean, there's some pretty fundamental definitions here I've defined, which will be hard to change, but I can always change how certain other functions are implemented. But the main sort of design choices here are just how the hierarchy I have of the different types of MDPs and, what is needed for them. In particular, the ones with a probability transition function, compared to the sampling MDPs here, where instead there's this step function defined. Yeah. I think also will be included here is a way to make the grid world construction function. So because I'm using it in all these examples, yeah, this is yeah, this will be included in there. And then I plan on adding an example notebook, which maybe has some other sample environments to choose from. But hopefully with the documentation, makes sense how to construct your own MDP from this. Yeah. So I don't know. It's sort of, I guess it's a lot to go through in one thing, but I think that is pretty much all I wanted to say about the primary techniques in the tabular section. Everything else is sort of, a lot of different implementation details and little tricks. Also, if you read, you can also read the summary of part 1, which sort of goes through its own perspective on the difference between the techniques and the difference between sampling and dynamic programming. But yeah, you can let me know if there's any questions or comments about either stuff that was confusing or ideas on how the code is structured. And you could also message me on Meetup or create a GitHub issue. Also, if anyone isn't in the Slack for this, there is a Slack channel for this group, which we sometimes use to make announcements or post stuff. So I don't know. If anyone isn't in the Slack and wants to be, we can share the invite link for that.